So this one now says prove, and we're going to do the whole thing here. And it's one of those formulas which we used earlier on in the course, the standard formulas. First thing I'm going to do is when n is equal to 1. When n equals 1, the left-hand side here is the sum from 1 to 1 of r cubed. So put a 1 in there. 1 cubed is 1, and stop there. And the right-hand side is a quarter times 1 squared times 1 add 1, which is 2 squared. 4 times 1 divided by 4, which is 1. So left-hand side equals right-hand side. Therefore, true for n equals 1. There's our first step 1 mark. We know it's true there. The next thing we say is assume true for n equals k. And write it down. So I know we're just repeating the question, but write this. From r equals 1 to k of r cubed equals a quarter k squared k plus 1 all squared. And if you want to, at this point here, we want to say then for n equals k plus 1, it should be, we're aiming for this thing here with a k plus 1 in it. So stick a k plus 1 in there, and we've got a k plus 1 in there, k plus 1 plus another 1. So that's what we're aiming for. But for the sum from r equals 1 to k plus 1 of r cubed is equal to the sum from r equals 1 to k plus the extra 1, which is k plus 1 all cubed. Right, this bit here is what we assumed was true up there. So we've got a quarter k squared k plus 1 all squared plus our extra bit. We're going to take out quarters, so I'm going to put 4 quarters in that bit there to help me. Take out the factor of a quarter. Take out the factor of k plus 1 all squared. Let's see what's left. We've got a k squared left there, and we've got a 4k plus 1 all there. That tidies up to give a quarter k plus 1 all squared, and this is k squared add 4k add 4, which just happens to factorize to be k plus 2 all squared. That was what we were aiming for. So now we get the statement right, and we'll read these a few times, read what the examiner's report says to get these things here. First of all, there was a statement, true for n equals 1. And if true for n equals k, then true for n equals k plus 1. That's what we just did here. If we assumed the first bit was right, then the second bit was right. So we can then sort of say, therefore, by induction, true for, now it's not everything, but it's all n belonging to the natural numbers. So we were proving it for 1, 2, 3, 4, and so on. We didn't prove any negatives. We've not proved it for fractions. It's just true for all whole positive numbers.